Hello everyone, today we're talking about solutions to systems and vector matrix equations. This is material from 1.4. So I want to recall the setup here. Suppose A, and I want to write the columns as A1 through AN. Suppose this is an M by N matrix. Then the matrix equation AX equals B has the same solution set as the vector equation. So what's the vector equation? Remember, I take those columns of the matrix. I want to write a linear combination. And I want to set them equal to B, and I want to find those x1, x2 through xn weights. Those are the unknown there, so that's the vector equation. And this has the same, which has the same solution set as the system of linear equations. So let me just write the system as an augmented matrix. You take that matrix A and you augment with the vector B. Okay, so we saw this last time, and I just want to maybe do another example of this today. So just, this can take many forms now, and you'll see in your homework that kind of asks the same question in different ways. So in particular, for example, I mean, like I said, there's many now different kind of combinations you can make to ask questions, but I can say that AX equals B has a solution if and only if B is a linear combination of the columns of A. This is one kind of flavor of statement that we could make. I'm going to do an example and then kind of give you a list of equivalent things. But let me do this example now. So this is kind of similar to a homework problem maybe. So for example, what if A was the matrix 1, 3, 4, minus 4, 2, minus 6, minus 3, minus 2, minus 7, and B was B1, B2, B3. It's an unknown thing. And what I want to ask is, under what conditions on B, on the vector B, is the matrix equation, equation AX equals B consistent? Okay, and so this is kind of weird because I didn't tell you what B is. B is somehow an unknown thing, but I want to know what are the conditions on that vector B to make the underlying matrix equation consistent. Now again, the idea here is we're going to translate this to a question about systems. So from above, what we know is we want to consider the system A augmented with B. So what is that? That's 1, 3, 4, B1, minus 4, 2, minus 6, B2, minus 3, minus 2, minus 7, B3. And I want to now, the usual story, I want to say, well, the idea is that, I want to know when is this system consistent. So we're going to reduce this to echelon form. And this will tell me, as usual, whether this guy has a solution or not. And we'll see that there's going to be a condition on the vector B that's involved. So let's reduce this guy. Let's see, that's my first pivot. So this will be 1, 3, 4, B1. To clear under the, in the second row here, I'm going to take 4 times the first row added to the second. So this is 0, what is that, 14, 10. And what do I get here? Well, I'm taking 4 times the first row, adding it to the second, right? 4 times B1 plus B2. For the third row, I want to clear this 3, so I'm going to take 3 times the first row. That's 9, 7. 3 times the first row added to the third, that's 5. 3 times the first row added to the third. So 3B1 plus B2, 3B1 plus B3. And now I want to clear here, right? Moving to my next pivot in my second row. I'm going to now, leave the first 2 rows alone. 0, 14, 10, 4B1 plus B2. Leave some room here. So what's going to happen now is I want to use that 14 to clear. So I'm going to take minus 1/2 of the second row added to the third. 0, 0. Now here's where it gets a little weird, is minus 1/2 of that second row plus what was there already, the third row. Okay? So this is now the third row of this matrix, which is now in echelon form. Right, and my pivots are these two. Now, I've got a condition here because it says that in the third row I've got 0, 0, 0 something. So as we know, to be consistent, to have a solution, what do we need? We need this thing to also be 0. We need 0 equals minus 1/2 4b1 plus b2 plus 3b1 plus b3. So in some sense we're done. Let me just kind of simplify this a little bit. So this is 0 should equal, looks like minus 2b1 minus 1/2 b2 plus 3b1 plus b3. So in other words, 0 should equal, let's see, we got 1b1 left, a minus b2, 1/2 b2 left, and a b3. Okay, and so that's our condition. So what this is saying is that for this equation ax equals b to be consistent, the condition on this vector b is that the entries of that vector satisfy this equation. So there's the first entry minus the half of the second entry plus the third should be 0. And that's the way you kind of do one of those. Let me end with kind of the fact that we've been sort of discussing here an example of, but the more general statement will be the following. So more generally, we have the following statement, which will be useful kind of as we're moving forward. So I'll call this a fact. That suppose A is an m by n matrix, then the following are equivalent. Now, what does it mean to say the following are equivalent? This is a kind of typical math jargon here. What it means is that if one statement holds, if one statement is true, one statement holds, then so do all the others. And I'm going to list a bunch of statements here. They're going to be equivalent in this sense. So the first one is for any vector b, let's say an Rm, the matrix equation ax equals b has a solution. Okay, so the first condition is saying that no matter which vector you give me, right? So you're thinking about A as some matrix that is fixed, that someone presented to you. And now suppose it's the case that no matter which vector you give me b, ax equals b, the matrix equation, has a solution. That's our first condition. It turns out that this is equivalent to saying, well, remember now, the matrix equation has the same solution set as the vector equation. So if we translate that, what that's saying is for any vector b in Rm, b can be written as a linear combination of the columns of A. Okay, remember now, if ax equals b has a solution, that means there's some x that always works here. Translating that to the underlying vector equation means that there's some way to find weights so that the columns of A produce a linear combination that equals b. Another way to say this was, well, if we're saying that any vector b can be written as a linear combination of the columns of A, it's saying that those columns of A get everything when we make linear combinations. Another way to say that is that the columns of A span Rm. Now to say that you span Rm means that the span, another way to say this, i.e. the span of the columns of A is equal to everything that you can possibly get, which is what we call Rm, all possible vectors. And then the last one is going to be kind of the most useful for us. So, in some sense, this is kind of conceptual stuff. We're kind of translating between these ideas. When you actually go to solve a problem like this, as we've seen, what you really want to do is, look at a matrix and do some row reduction. And so what we want to say is, in terms of pivots, we're going to say that A has a pivot in every row. So when I'm now going to look at this matrix, if this is the matrix A, I don't know what it looks like, but it's going to row reduce to echelon. And so in our echelon form, what we want is that there's a pivot in every row. So I don't know where they are, but what that's going to say is that when you think of A as a coefficient matrix, and when I augment it with something, no matter what it is, right, I'm not going to have this inconsistency problem. I'm never going to have a 0, 0, 0, 0 something because I've got a pivot in every row of the coefficient matrix. Okay? So this is, again, a list of equivalent statements. If one holds, then they all do. And, like I said, in practice, this is going to be the kind of way we actually calculate the thing. So that's it for now. We'll see you next time.